Happy Tuesday, P-Bio folks. We're going to continue talking about energy today in terms of the laws of thermodynamics. Thermodynamics is the study of energy transformations, and the really important thing for AP Bio is just that you understand the first and second law of thermodynamics and how they apply to living things, and realize that all living things and all of the processes in living things have to follow these laws, just like any other physical process within the universe does. The first law of thermodynamics has to do with energy transformations. Basically, this is the law of conservation of energy. The amount of energy is constant. The amount of energy that goes into a reaction has to equal the amount that comes out. And this is true of all chemical reactions. So here's photosynthesis as an example. The amount of energy that comes in as sunlight and within the bonds of the molecules is equal to the amount of energy that comes out stored in the bonds of those various molecules. The same is true of matter. That's a different law. That's conservation of matter, but both matter and energy are conserved from the beginning of this reaction to the end. The form of energy, however, is not constant. It's transformed every step of the way. And we'll be talking a lot in this unit about those energy transformations. You can see several examples down there at the bottom. We'll talk about the energy transformation from sunlight into chemical energy stored in plants. That's the process of photosynthesis. And when we break down our food in the process of cellular respiration, some of that turns into heat that we use to keep our bodies warm and is also lost to the environment. And some of that we use for various different processes, such as motion. So we turn that into a bunch of different types of energy, like mechanical energy and heat energy and all of those types of things. So energy can be transformed in many different ways, but the amount is constant. So that's the first law of thermodynamics. The second is a little bit more complex, but it's a concept that you're already familiar with. We've talked before about energy pyramids and the fact that as energy flows from the sun into plants, up through herbivores to decomposers, at each step along the way, some of that energy is lost as heat. And so another way to say that, you will hear this term a lot today. The idea of free energy is actually a little bit misleading, because free energy refers to energy that is useful to life. So when you hear the word free energy, I actually want you to think available energy. Or you can think of it as energy in chemical bonds. Not like bank bonds, but like chemical bonds, like stored in a molecule of glucose. So energy that's useful is available to living things, and it's stored in chemical bonds. So that's free energy. But if it's just the energy of atoms that are moving around, that's not useful. And that's what's listed in this diagram as heat. So all the way through here, energy is lost as heat. And like we talked about in ecology, that's why there can't be 15 trophic levels going up an energy pyramid. Most energy pyramids end after 4 or 5 links in the chain, because there's simply not enough free energy or usable energy to support more trophic levels. And that idea brings us to the second law of thermodynamics, which is that no physical process is completely 100% efficient. It doesn't end with the same amount of free or available or useful energy. Some of that energy is lost to the random movement of molecules, which can also be described as entropy. Entropy is a word that basically means disorder. So the random movement of molecules increases the amount of entropy or disorder in the universe. And so this could be a transformation to heat, transforming that energy into heat, which is just kind of lost to the environment and is no longer useful to living things. It could mean that big molecules are breaking down into smaller ones. That's more entropy. A bunch of small molecules are less, the atoms are less organized and less ordered than if they're all attached in a big one. Or an ordered system becomes more disordered. All of those are examples of increasing entropy. The second law of thermodynamics is often referred to as the law of entropy. Entropy is always increasing overall. Now, keep in mind, when a living thing grows, as it builds bigger molecules, as it builds proteins, as it builds cells and organizes those cells into tissues, those types of processes actually decrease entropy. But they still don't violate this law because overall, the net sum of all the interactions happening within a living thing still increases entropy in the universe. Our bodies are giving off heat that's increasing the entropy of the universe. And that type of activity offsets that, and the molecules that we're breaking down as we digest food, those types of things offset the other. So overall, there's still a net increase in entropy as a result of all the processes of living things. Here's a way that this type of reaction is often visualized. You're going to see a lot of graphs like this, and there's a lot of vocab words in here as well. In this graph, you will see the x-axis shows the progress of the reaction. So that's just beginning to end. There's no specific timeline or anything like that. The y-axis shows you the free energy. And remember again, free energy means the energy that's usable and available, and the energy that is in chemical bonds. I'm going to write that again here because that'll be important to remember as we talk about this. So in this case, the reactants have a lot of free energy, or a lot of energy stored in chemical bonds. The products have less. Sometimes you'll see these drawn as line graphs, kind of look like that little downward slope. If the reactants have a lot of energy stored in chemical bonds, that probably means that the reactants are bigger molecules that have a lot of chemical bonds, maybe like a molecule of glucose or a more complex carbohydrate. And the products are smaller molecules that have less chemical bonds. They have fewer chemical bonds that store less energy. And so as those big molecules are broken down, there is a net release of energy here. Some energy is given off into the universe in some other form. And that energy could be captured in another molecule, or it could just be released as heat. So this type of reaction releases energy. The word for that is exergonic. That's an exergonic reaction. It releases energy. And in this case, the change, there should be a delta sign in front of this, the change in free energy, G represents free energy. I'll just write that over here. Is negative because remember, to figure out delta G, to figure out the change in something, you would take final minus initial. And so if you take a small number and subtract a big number, you're going to end up with a negative change in free energy. It's decreasing. Negative means it's decreasing. Because of that, because this releases energy, these types of reactions will happen spontaneously. The easiest way to remember that is if you put a ball at the top of a hill, it will roll down spontaneously on its own without you having to do any work, right? So reactions that break big molecules down into small molecules will happen spontaneously and will release energy and have a negative delta G. There's actually an equation for how to calculate free energy that used to be required as part of this class. You don't need to know the equation anymore, but you do need to be familiar with the concept. And of course, we also have a graph that has the opposite of all of this stuff. So same deal, progress of the reaction on the x-axis, the amount of free energy or the energy stored in chemical bonds is on the y-axis. So here we're starting with small molecules that only have a little bit of energy stored in bonds. And we're going uphill. We're building larger molecules. So here we have small molecules with just a little bit of energy stored in a couple chemical bonds. And we're building larger molecules that have lots of energy stored in a lot of chemical bonds. So in this case, we need to put energy in to make this happen. So all of the things that we said before are opposite for this one. This one requires energy. You're trying to push that ball uphill this time. And so that is going to require energy. It is not going to happen spontaneously. And the word for that when energy is required, this is an endergonic. Think exergonic, like energy is exiting the reaction, and endergonic, energy is going into the reaction. And again, there should be a delta in front of this. The change in free energy is positive. It is increasing from the beginning to the end of the reaction. You're going to see graphs like this frequently and hear a lot of these vocab words, and we're going to continue reviewing these over the next couple days. So you'll have some more chances to kind of practice with this vocab, and we'll continue to make connections between all of these things as we start talking about specific examples with things like photosynthesis and cellular respiration, which will be the bulk of this unit. Okay, so now you have a whole bunch more information and vocabulary about energy in living things. And so to continue working on this, you're going to go back to the chemical reactions packet that you were working on yesterday and try and work through the rest of it. Notice on here that you may skip questions number 16 and number 19. If you would like I said, you will see the equation for free energy in this packet. You do not need to be able to do calculations with that equation. You just need to kind of understand the concept of free energy. 16 and 19 get a little more into the mathematics of it, so you may skip those two questions if you would like. Discuss this with people if you're able to. Research the terms that you don't know. Preferably start with your bio textbook. This is chapter 6 in your textbook if you're looking for some information to help you, and see if you can understand and explain these things as best you can. Shoot me an email if you have any specific questions, and I will see you again tomorrow. Have a great rest of your day.